Hi, we are going to compute the next double critical day um, according to this biorhythm thing. And all it means really is that we have 3 cycles of 23, 28, and 33 days, and if 2 of them meet each other, then it's called a double critical thing. Um, we start counting from a birthday, and then it has to be the first time they meet. Any 2 of them meet after a given date, supposedly like today's date or something. Um, and then there's a red herring here. It says the triple critical day, which you're also supposed to check, but it doesn't matter because a triple critical day is of course a double critical day as well. There's 2, and there's one more of these cycles meet. We are supposed to take input and give output as year, month, day vectors, and that's really all there's to it. So the cycles are stated in as 23, 28, and 33 days, but think of a sine curve. After the whole period, then we cross the x-axis again in the same direction, but we've already crossed in the opposite direction once. So the actual cycle we're interested in is actually has half the period of the given periods. Now let's find out uh, what uh, number of days we have to progress before we have 2 of these. And we can do that by finding the least common multiple. So let's make a least common multiple table of these. Of course, we're not interested in when a cycle meets itself. It does that every time it crosses over, and we've got duplicates because it doesn't matter which one comes first. So we just need the upper right corner here, and then we can do that. So let's generate the vectors from 1 to 3, and then we make a comparison table, and for that, and that gives us an upper right matrix, and that's a good mask for the matrix on the right. So we can use filtering or compress, or replicate if you want to call it that. We just need to flatten both first, and then we get these. These numbers are stated in the problem statement as well, but now we know why it is exactly these numbers. So we can uh, we can call these the periods, I guess. An example input 1962 October 31st and 2023 the 1st of January, and now we can start coding. The first thing we need to do is we need to transform these dates into a serial number of dates so that we can do computations on them. So for now, let's just say we concatenate them together, but we pre-process both arguments with the conversion. And for that, we have to treat each one as a whole. We call the datetime conversion function, and it assumes that it's a timestamp like this. So we don't have to tell it what the input type is. We just need to tell it the output type. And type 1 is a day count from the beginning of 1900. So that gives us these, and that means we can find the difference here between them with minus instead of concatenation. This is negative, of course, because we have a larger number last. We could swap the arguments to get the positive difference between them. And now we need to find out when the next day is. So we need to find a whole multiple of these cycles from the first date. So we can see how many of these cycles are there from and from the first date to the second date, and then we need one like how many whole cycles are there, and then we need one more date, and this calls for a modulus operation. So if we take p here and modulus, so this means the remainder when with this over here, when the difference between them is divided by these periods, and that gives us these values. But this is how much is left up until the and the last chance before the second date, right? That's what remainder means. But there's a clever thing in the definition of the remainder in APL, and that is if you negate the right argument, then instead of stopping right before the cutoff, we stop right after the cutoff. We can't really tell that immediately here, but if we try it, we can see if you call this one B and this one A, then if we add together A and B, that gives us the P that we have from up here. So we can see that by negating on the right, we get one more cycle, so just after the cutoff. So that is actually what we're after. Now what remains is that we don't want to know how many days after the current date, the date on the right, it happens. We want to know the actual date. So we take the date on the right, and we add that offset we need to go beyond that date. We need to find the first thing, which could be 0 if it's evenly divisible. So now we have these date numbers, and all that remains is to convert the other way, so that's -1. So we're converting to a timestamp. And oh, we forgot one thing. We have to find the first one of them. It doesn't matter which one. So we can, before we go here, we want to take the lowest one, and then it will make the formulation easier to realize that we're doing a reduction over a vector on a scalar function's result, and that can be combined into an inner product. It's exactly the same thing. Okay, now we can convert to date. And it's enclosed. Remember, we enclosed this to treat it as a whole, and that's the same thing over here. So we're going to disclose here for that's our effect to get the whole thing. And then it has date and time, and we're not interested in the time, so we just need to take the first three elements from that. I'm binding these two together because we have a monetic function here, so it fits in the train form. And now we can actually go and define our function directly. We could we can put in the actual value of over here and get rid of these given arguments. Oh, you still need the parentheses over here, and we have our function, and then we can call our function with these arguments. And just for good order, let's see what happens if we give it the same argument both sides. Then it should say that that date itself is its own critical date, because all the curves start there, so they kind of intersect there. And that's really all there is to it. Thank you for watching.